Well, good afternoon, everyone. Good morning, good afternoon, wherever you may be. Thank you very much for joining us today. My name is Toussaint Myrix, and I am your host for this Department of Energy National Lab Discovery Series webinar. And today we'll be exploring a very interesting software innovation codenamed Fenix, an advanced open source multiphysics tool, which was developed here at the Idaho National Laboratory. In addition to serving as your host today, I'll also discuss some brief insights on forming strategic partnerships with the Idaho National Lab. Today we're privileged to have the researchers who are behind this software, Casey Eisenhower and Pierre Clement Simon, who will be presenting and giving us a good overview of the functionality of the application. And they will share their expert perspectives on this technology. Before we proceed, I'd like to remind you that your microphones will be muted during this presentation. And if you have any questions, please type them into the chat box at the bottom of your screen, and we'll address them during the webinar Q&A session at the end. So now let's dive into the fascinating world of Fenix. Casey, Pierre, Clement, please proceed.
Hey, hi everybody. Yeah, good morning, good afternoon, good evening, wherever you are. First of all, I want to say thank you very much to everybody for joining in. It's a very exciting and busy time for Fusion, especially this summer. So really appreciate everybody taking the time to join us. I also want to say thank you very much to Sean from the DOE Office of Technology Transitions for having us and inviting us. And thank you to Sean for monitoring this session. I hope everybody can hear me okay. Otherwise, use the chat if you want to make any comment. But maybe we can start with introductions. I see one hand raised. I don't know exactly how we want to handle those. I think what we'll do is if you have a questions, you can put it in the chat and we'll address it. Then we might have more time for Q&A at the end of the So hi everybody, I'm Pierre Clement Simon. I go by PC. I'm a computational scientist and field performance modeler at Idaho National Lab, which I joined in 2021. And I'm the lead PI for Fenix, which is the code that we'll talk about today. Casey, do you want to introduce yourself?
Yes, thank you. Like PC said, very happy to be here to talk to you about the work we're doing in fusion energy modeling and simulation. I'm a computational scientist at Idaho National Laboratory. My name is Casey Eisenhower. I've been at INL since 2018, originally as a student in our graduate fellows program, and have since converted to staff in 2023. So happy to be here.
Yeah, let me share my screen. Casey, can you let me know if you can see it?
I can see it. Yep.
Awesome. Yeah, so today we'll talk about Fenix. So Fenix is an open source multiphysics integrated framework to enable collaborations for the development of plasma-facing component modeling capabilities, but also we have as a goal to go deeper into the blanket. So the subject here is for technology transition, and sometimes there's a little bit of confusion when we talk about open source, that this idea that everything will be immediately shared with everyone, and that it's very difficult for private companies to have any interest in those tools. But stay tuned for that, because we'll present ways with examples on how, even though Fenix is open source, private companies can definitely leverage it and have a lot of ownership and control over their own development. So we'll talk about that a little bit. But to go right into it, first I'll give a very brief overview about what Fenix is and what the goal of this project is. And then we'll make the very strong point that Fenix is a Moose-based application. And so it's very important to understand Moose and understand its capabilities, and especially the success it's had in the fission nuclear space, and how we plan to not necessarily apply this directly, but leverage those successes, those tools, those lessons learned through Fenix for fusion applications. And we'll talk a little bit about how we ensure high software quality assurance, how we have a flexible license, which will be key to technology transitions and enabling all of our partners to benefit from those collaborations through Fenix. We'll talk about how modular those capabilities are, and we'll present some examples of successful collaborations, including private-public collaborations and international collaborations. And then we'll talk a little bit about how you can get started with Fenix so that you come out of this webinar knowing where to go. The goal here is not to present all the capabilities, and I'll say it up front, it's not because Fenix is open source that it's completely done and there's not going to be any development. On the exact opposite, the reason why we put it open source is because we want the whole development of Fenix to happen in an open manner, in a transparent manner, and with the collaboration of the entire community. So I wanted to make that statement before we dive in. So what is Fenix and what are we trying to accomplish here? So Fenix is a product of an ongoing ALDRD project. And what we're trying to do here is understanding the interactions between the multiphysics and the materials around the plasma-facing component. And so we're creating that framework that, as we said already, leverages MOOS, that you can see. I think I'm going to try to use the laser here. Leverages MOOS, that is a finite element method framework that does multiphysics, has been recognized with the R&D 100 award. So we leverage some existing capabilities like heat conduction, thermal hydraulics, thermal mechanics, and we're coupling those with new capabilities. So TMAP 8 is an example of that. We'll talk a little bit about what TMAP 8 does, but basically MOOS-based tritium transport. But then because we want to see the interactions, with all the multiphysics, we also are developing capabilities for neutronics calculation through Cardinal, and we'll talk about that code too. Also a recipient, a winner of the R&D 100 award. And then we also aim to develop some nascent plasma kinetics capabilities through particle and cell to make sure that we're able to really understand the interactions between all of those physics. But first, before we go deeper into Fenix itself, I think it's important that we give a detailed background of what MOOS is specifically. And so I'll let Casey do that.
Thanks, PC. As part of my work at the laboratory, I'm on the core MOOS framework development team. And I just posted a URL that you can go to check out what MOOS is in more detail in the chat. But MOOS, the goal of MOOS is to accelerate the development of high fidelity modeling and simulation tools. And I say high fidelity here, but we're also talking about multi-fidelity as well. We started MOOS, this was well before my time at the laboratory, but MOOS was started with the idea of whole reactor core modeling for fission systems. And so we have this rather old cartoon at this point showing the core idea, bringing together different physics into a single system that's modular and complete, and then open source so that folks and researchers and students and industry partners can pick it up and use it, which we believe adds to equity and inclusion in science, engineering, and research. MOOS was designed using modern computing practices and intended for use on everything from a local workstation to massively parallel high-performance computing simulation. We have high software quality assurance practices as well. I help lead some of our software quality assurance compliance to the Nuclear Quality Assurance Level 1 standard. And we're also holding those standards at the Fenix level as well. So with respect to Fenix, you're getting everything with MOOS, but you're also getting specific capability that we've developed on top of that, leveraging this modularity and flexibility. So let's go to the next slide. MOOS was developed under the DOE Office of Nuclear Energy Advanced Modeling and Simulation Program, or the NEAMS program. I bring this up because I think that utilizing tools from other areas of the Department of Energy, other areas of public investment is a really important thing to consider when creating new designs for fusion and wanting to push toward deployment. So this program is across several national labs and focused on advanced reactor design and analysis, split up into different technical areas. So this primarily leveraged Moose for the software development. And if we go to the next slide, we see several. Oh, I guess we got the order a little mixed up. So all of these tools, and we'll talk more about those in a moment, all can work in concert. So going back to Moose, all of these NEAMS program tools leverage some combination of the Moose physics modules, all of which are contained within the Moose framework itself, and all of which are also open source. So we've highlighted a few in bold here that might be most representative of what you might want to bring together in order to perform a fusion simulation. So we've got electromagnetics and heat conduction, heat transfer, Navier-Stokes, particle tracking, porous media flow. I want to highlight in particular some of our non-physical modules. So we say physics modules is the umbrella, but we notice that we have a few here that are more topical area modules. So stochastic tools is our stochastic analysis module, and that brings in the capability to take the high fidelity modeling or medium fidelity or low fidelity modeling that we're doing with Moose, and then further creating reduced order models based on that for further use in design iteration. We leverage the PyTorch or libtorch code in order to also bring in machine learning. So an arbitrary combination of all of these can be used to create new things, and we kind of see these as building blocks, starting small, building to a bigger outcome. Go to the next slide. So going back to NEAMS and how it accelerated a fission reactor deployment, Moose is our general underlying framework, but through the NEAMS program, we've developed very focused applications for different aspects of the fission problems, like Bison for nuclear fuel performance or Marmot for mesoscale materials. All of these, because they're based on this common and integrated framework, can work in concert together. And it's allowed us to collaborate with regulatory partners as well as industry partners to facilitate their deployment. So the modularity of Moose and the license we've chosen, LGPL version 2.1, enables public-private partnerships because you can reuse code with proper attribution and create your own flavors of it based on your specific design needs. So one great example is the Kairos Power version of the fuel performance code Bison, so KP Bison. They were able to work with INL to obtain a license to the code and then use it to create a version of it specific to their TRISO fuel concept, which they're then proceeding with use for their regulatory licensing and that process. So they're able to take what we've developed with public investment, but then further developing it privately in order to design and create their products. Let's go to the next one. So one last lap for how modular systems enhance flexibility. We've got several different examples here of very different kinds of fission reactor concepts. Everything from molten salt fast reactors to TRISO particles in a graphite compact to the HTTF concept. I show all this to say that with these general components brought together in very specific ways, influenced by your use case and design needs, you can create very, very complex simulations to help you create the products that you desire. So with that, I think I'll give it back to PC for a further discussion of Fenix.
Yeah, thank you, Casey. Oh, somebody else trying to join. So course, the computer is now lagging. Okay, sorry for that. Hopefully you can still hear me. I had the tiny wheel of death for a minute.
Yeah.
Okay.
Yeah, we can
Thank
hear
you. Thank you. Just want to make sure I don't go on, on my own. So the idea here is really to leverage some of those successes in Fusion, using that modularity, using the same licensing approach, using the same software quality assurance solutions and frameworks that are already developed in Moose, and all those capabilities that exist. And so here I'm showing again what we try to do with Fenix, and hopefully you get a better understanding of what the goal is here and what the approach is, because it's similar to what has been done for other fission concepts and other fission challenges. So here the goal is to create a flexible framework that can really create a pathway for fully integrated modeling of whole device. And we have the chance here to work with universities like NC State and UIUC, but also international partners that UK AEA, and we'll talk a little bit about that later on. But the first thing, so when we talk about Fenix, as I said, we also couple to existing tools like TMAP 8. And I want to spend a little bit of time talking about TMAP 8 specifically. So TMAP 8 is the Moose-based version of TMAP 4 and TMAP 7, which existed for tritium migration. They were widely used, but they have significant limitations, like only being able to do 1D simulation, having a limited number of trapping species, etc. So TMAP 8, by leveraging all of the Moose capabilities, is able to perform a high fidelity or even low fidelity, but flexible fidelity simulation at a multi-scale in 0D to 3D multiphysics simulations of tritium transport. TMAP 8 is also developed open source. It's following the same software quality assurance level, which I think is very interesting or very valuable to users, because that the code has been developed in a very robust manner that is thoroughly tested, etc. We also offer user support, because a lot of the issues that come up can be solved by TMAP 8 developers, also Moose developers, and it also offers massively parallel capabilities. I show here some examples of the type of simulations we can do, really going from what you see on the right with some ceramic materials, really at the pore scale, and looking at tritium transport at the pore scale, and extrapolating that to simulating a whole section of the blanket and how tritium is transported in the blanket. I also want to emphasize the big effort that we've been putting in place for verification and validation to show the robustness of the code and the model. And actually, I think we can just go to the TMAP 8 website. I think Casey is going to share a link in the chat. But if you go to the TMAP 8 website, you'll find instruction on getting started. We'll talk about this later. But what I want to highlight here is some verification and validation cases. Those familiar with TMAP 4 and TMAP 7 will know those. But we basically here, let me take an example, just this one, just to see. So we just describe some of the cases, describe what we do, explain the analytical solution, and then show the match between TMAP 8 predictions and the analytical solution. And then all of those input files are available when you download the code. The other thing that we have is some example cases where we have an example of calculating the fuel cycles to have an idea of the tritium inventory that you have. A recent paper from Masashi Shimada, the head of the fusion safety program at INL. He was here modeling diverter monoblocks and tritium transport in diverter monoblocks. And so we go here through what the problem is, how we solve it, how to build the input file, what the results are, and what they mean. So if you want a place to get started, those are great resources. So this is kind of what you have when you use this kind of tools and TMAP 8 in particular. So I'll move on to another code that we use a lot in Fenix is Cardinal. So Cardinal again is a solution that is applied to fission and fusion simulation. And the one thing it really highlights is how Moose can wrap around existing capabilities, existing codes, to perform those multi-physics simulation. So Casey talked a lot about how we have capabilities existing in Moose that can be leveraged. But if something is missing, and for example here, NECRS and OpenMC echoes the capabilities that were missing, OpenMC especially for neutronics, that we're missing, and we can wrap around those codes to be able to then, in an integrated manner, do multi-physics simulations. So I wanted to highlight that, and Cardinal is also a R&D 100 winner. And you can see here it's definitely not design specific. Here we can see images of it being applied to a wide range of systems, including fusion systems. Casey, I think you have your hand up. Do you want to add something?
Yeah, I do. I want to make it clear to the audience that we're talking about these separate codes from Phoenix, but all of Phoenix contains this capability as well. So when you want to run a TMAP8 simulation, because TMAP8 is integrated into Phoenix, you can also run that simulation at the level of Phoenix. So it gives you a pathway to create like this on-ramp to start with one set of capability in an input file, and then build that over time to create this really complicated simulation. Again, leaning back towards modularity.
Yeah, thanks, Casey. Thanks for highlighting that. So some effort that has been going on, and this is work that is done by Mahmoud at UIUC. He's also doing an internship at INL this summer. And what he's been focusing on is doing some preliminary calculations of neutronics coupled with other physics within Moose. One of the main highlights of this work so far is that he's been able to create a workflow to use CAD geometries directly in OpenMC and Moose. So this is kind of what's highlighted here when you do OpenMC simulation, transfer the heat source, do calculation of heat source, but also tritium generation rate, as you can see on the top here. And then you can do all of those calculations in Phoenix with tritium transport and heat conduction, etc., and then send back the temperature for the OpenMC calculation. So this is how this is really enabling those multi-physics calculation on CAD geometries. And here's an example of some of the capabilities that we developed, and this is Grayson from North Carolina State University, who's also doing an internship at Idaho National Lab this summer. And he's developing those nascent particle and cell capabilities, and in the meantime, developing a suite of verification and validation and benchmarking cases to demonstrate accuracy of those capabilities. So here he shows, for example, when you change the time step of your resolution, you get closer to the analytical solution and you show convergence. And here what he shows is uniform generation of particles, and then the resulting electrostatic potential in 3D. But this is really I think this is one of the most important slides of today, because this is where we make the point that the modularity and the licensing approaches that we use here is what enables those public, but also public and private partnership. And how even though Phoenix is open source, it can be leveraged by private companies with a great amount of ownership and control over their own code development. So one thing I wanted to highlight here is that Phoenix is design agnostic. I think we made that point, is that Moose is design agnostic. It's not related to one geometry or anything like that, on the opposite. So you can apply it to a wide variety of systems. And then Phoenix, like Moose, uses this license that makes it very, very flexible. And this diagram is kind of highlighting the kind of things that is possible here. So we have ongoing right now, so Phoenix is open source and it's hosted at INL, but we have open collaborations with universities, with other national labs, etc. And so that enables very easily, we can collaborate with universities. You don't need to go through an export control, process. So, when you have somebody starting a PhD or just a master or doing a postdoc, they can have access to the code immediately and start working on it. But then and then contribute to the code and benefit also from everything else that everybody is doing and contributing to the code. But on the other end, the need of private companies can be very different, where you need a lot of ownership. If you create a mesh, for example, you don't want to share it with everybody. If you develop some material models, material properties, and parameters, you don't want to share it with everybody, and that's completely fine. You can have your own version of the code locally that's private, that you have full control over. A little bit like the example that we gave earlier, like KP Python for Keras Power. And you can leverage that, and so you can take in benefit from everything that is being developed, open source, with the entire community, and you can send back some information, you can send back some capabilities if you want, but I also want to highlight that you don't have to, and you still have ownership of the code and capabilities, and you can use it for regulatory tasks or whatever you want, really. And that's really what it enables. The other thing I want to mention here that's really important is that since Fenix is open source and we have collaboration with universities, it also really supports talent development. And if you have a student, for example, that goes through a master or even a senior design project or a PhD, they'll be trained on Fenix, they'll be trained on Moose, and they'll be able to start with that, even if they go to that company, they'll be able to start working on the code immediately. They would not have access to anything the company was working on exactly on the code, but they'll know how Fenix works, they'll know the current open source capabilities, and they'll be able to contribute immediately. So I think that's really a key aspect here of talent development. Casey, do you want to add something here?
No, I think you really said it well, that our goal in the Moose project as well as Fenix is to enable the future fusion energy workforce. We believe that the way to do that is through thoughtful licensing, high community engagement, high software quality assurance practices, and flexibility. And flexibility is key. So if you adopt Moose or Fenix in your workflows, know that you're getting this collective experience, great public investment, and great interaction with the wider community, and that's what we'd like to bring to bear to the Fusion community as well.
Yeah, and this is the example of such partnership with the UK AEA. So they were very interested in performing some multiphysics modeling to support some of their own development and research needs. And so they started using Moose and started developing tools on their own, actually. Funny enough, INL was not really involved in facilitating this originally. Now the UK AEA has become an active partner, and we've been collaborating with them quite tightly. But that really shows that even a different institution from a different country can leverage those tools and benefit from it, and then they can decide whatever they want to contribute back and whatever they want to keep. There's a lot of flexibility in that. And I put a reference here for those who are interested in learning more. But I want to go now to how to get started with Fenix. So we have the QR code here, but I think Casey is also going to put the link in the chat. And I'll go to the Fenix website. Hopefully everybody can see where I am right now. And so this is the website that is open source since the beginning of the week. So it looks a lot like what you'll see on the Moose website or the TMAP8 website. And here what I want to emphasize is, we have extensive documentation of the capabilities that we have. So you can see here all the different capabilities that are in Fenix, but also inherited from Moose. I won't go through all of them because that would take several days. But we also have extended documentation about the software quality record. So you can go through all of those items if you're interested in that. But also, how to get started. We have some instructions here on how to install Fenix on your system versus your local machine or HPC capability. And so we try to be very thorough here so that people can just follow those instructions and get started with Fenix in a few minutes. We also have some instructions about how to use Fenix, how to run input files, what do we, what are the kind of test verification validation do we have? And also we have a page to contribute back to Fenix where we explain exactly how people can do that. So what we try to do here is really lower the barrier to entry so that even, students that start their master without an extensive experience in C++ or extensive experience even in modeling and simulation tools can't get going. And as we said, we try to provide test, verification, validation, example cases that can be used as starting points to just get going. The other thing I wanted to highlight here, because we haven't talked about this yet, is the continuous integration approach that we use in Moose and Fenix. And so this is an example here of, Grayson, who's working on developing the plasma capabilities. So he wanted to make that change. So he wanted to add capabilities for charged particle motion in electric and magnetic fields. And so what's happening here is that, Grayson on his local machine will make those changes, and then we'll want to push them to the code, right? And so what's happening when he does that through GitHub is that GitHub will help us automatically generate a lot of information. So it'll create the documentation that we need to make sure that everything is documented and we can open this. But also, as I said, we have thorough testing of every capability. And one of the things that we get out here is we check the coverage, the test coverage. So for example, 94% here is 94% of the lines that were added to the code were hit by a test. What that enables us to do is if there is a new contribution that is not tested, which means, it hasn't been checked, then we can check that. Casey, I see you have your hand up. Do you have a question? Oh, something to add?
Yeah, I wanted to make a comment about this. So GitHub, is a public-facing website, run by Microsoft, but they have APIs to allow us to. So this is generated by INL testing systems internally that builds a copy of our website for you to check the documentation, because the documentation is actually built into the code base. Coverage testing and access to those reports for you to evaluate. So that's what we do for Fenix. If you're developing a Moose-based application that inherits from Fenix or inherits from another Moose-based tool, we're unique in regard that we actually do try to make sure we don't break you, and we do this by allowing external institutions to use our continuous integration system. So if you were to create a Moose-based application yourself, and you communicate with us, and if it's open, or even we do have a few that are controlled, that we can interface our testing infrastructure, which runs millions of tests per week, to suit your needs here.
Yeah, thanks, Casey. Yeah, and the other thing we check is that new capabilities will not break previous capabilities, right? So that really ensures robustness in the code. That once that change is merged, it's not going to break anything that was pre-existing. And so what you see here is Grayson is contributing, and then I provided the first round of review, and then we have Logan here, who's another collaborator here, provided another round of review, making suggestion on the type of code, okay, a little bit of cleanup, and then there's a little bit of back and forth. Which I think really helps us collaborate with people outside of INL, where we can just help people out. If, for example, if it's your first contribution, it might be a little bit daunting for some, and we can guide that process. And so we go back and forth until all the tests are passing. So here's an example at the very last part. Every time there's a new commit that comes in, we run all the tests. We run the test in debug mode. We do some pre-check to make sure there's nothing that's going to break. We build the documentation, making sure there's no broken link or anything like this. We check the coverage to make sure that everything is being tested appropriately. And then eventually, when the change control board here was Logan and I, approve those changes, then we can merge it. And we know that as we merge it, it's not going to break anything else, and the code is going to stay robust and running.
And I want to add one more thing to this. So while this may not surprise anybody that's worked in software development in the past, for a lot of engineering codes or even basic science codes, when the Moose project was started, this wasn't necessarily the norm. Agile software development and open, transparent software development wasn't necessarily the norm here. And so we prioritize that transparency and these development practices, which I still think is a big selling point for our approach.
Yes, and I'll add too that those discussions here, now that the development of Phoenix is open source, are going to be open. So the development is transparent. Anybody, even anybody can connect here on GitHub and chime in. If there is something that should be changed, etc. Those discussions can involve a lot of people that are outside of INL that just want to contribute to the code or are interested in that particular topic. So that's really something that enables community engagement as well.
Yeah. These pathways for interacting with us, by the way, are all built within the GitHub repository itself. So either by creating an issue or creating a discussions post in the same place that you'll find the code.
Yeah, and I'll point that on the website. Help here, you can create the issue, reach the discussion forum. And also, if you don't want to use Phoenix, but you want to reach directly the Moose folks, then that's available. And that's something I'll mention too, is sometimes when you have an issue or a challenge, or you want to do something with a Moose-based app, you not only have the community of that specific application to help you, but sometimes you also have the whole Moose community that is available to help you. A lot of the questions I personally have when I do development can be answered by Moose folks, and so that really multiplies the amount of people you can work with and learn from. But in conclusion, hopefully we made the point that Moose is a proven system for complex multiphysics analysis and really helps accelerate nuclear research development, demonstration, and deployment. And so what we want to do is, through Phoenix, because it's Moose-based, is leverage those capabilities to support high-fidelity modeling of fusion systems. And we really believe that this open source strategy enables effective collaborations, but also promotes inclusion, diversity, and transparency, and the development of a broader workforce for fusion, which is going to be crucial for the success of this industry. And again, hopefully we also made the point that this flexible licensing approach is key for successful public-public, but also public-private partnerships. And I think as the last message, those flexible frameworks hopefully will create a pathway for fully integrated whole device modeling. I want to spend a little bit of time acknowledging all the people that work on this. It's obviously not just Casey and I. There's a lot of folks from a lot of different institutions. I put the logos here. We have the chance to work with a lot of universities and partners in the US, but also internationally. And we want to acknowledge some of the funding sources and also the high performance computing systems that we have at Idaho National Lab. And that's it for today. Hopefully that answered all of the questions. And if you have more, then use the chat and we'll engage there.
Well, thank you very much, PC and Casey, for that very informative presentation. It provided a great overview of Phoenix and its ability to leverage the Moose framework. I'm looking forward to a robust Q&A session afterwards. Now, before we move on to that Q&A session and hear more from Casey and PC, I'd like to take a moment to discuss how businesses and other organizations can partner with the INL through technology licensing or other forms of strategic partnerships. So if you can just indulge me for a quick minute, I'd like to give you all an overview of what we do in our portion of the lab. Just a quick second. So, as I mentioned at the top of the session, my name is Toussaint Myrix, and I am a senior software commercialization manager here in the technology deployment department. And so, stepping back for a quick minute, it might be fair to say that, or at least certainly two individuals who are more prominent than I am, two Nobel Prize winning economists, have indicated that innovation is responsible for 80% of the country's economic growth. And the innovation seems to be, if we were to think about it um, conceptually, is a combination of technology, capital, and labor. And it's a driver of economic progress and a driver of technological improvement. What we think about is, okay, so we've got the bright idea, but really the value of an idea lies in how it gets used in industry. So we try to think through effective ways and strategies for moving these very important and valuable innovations out of the lab and into commercial application. And historically, the federal laboratory system and the federal government as a source of funding has been a pioneer in developing and bringing to the commercial markets a wide variety of technological innovations, from cellular communications, which came out of the military domain, touchscreen technology out of the DOE and CIA, and as well as the DoD, the internet, originally called the ARPANET, funded by the DARPA agency, the Defense Advanced Research Projects Agency, Siri, fingerprint recognition. Many of these innovations started with federal government funding in federal government laboratories. So it's probably no mystery. What you see here is a quizzical sign, a picture of the old days, but INL is perhaps best known for its work in the nuclear sector, for being the place where nuclear reactors were first created. But our focus here in the technology deployment department is on commercialization, and that's commercialization in all the domains that are a focus for our scientists and researchers here at INL. And that includes making INL's assets available both to industry partners, to other universities, and even to other national laboratories in specifically physical assets, human assets, such as the know-how that goes along with these innovations, and the intellectual assets that we've developed over time. You've heard a considerable amount about Moose today. There's also other software innovations like RELAP, which deals with our reactor excursion and leak analysis program for modeling and analyzing some of the dynamics of operating nuclear reactors. So we're active in a number of domains that are central to our core mission, which is to ensure that we're developing and achieving maximum societal impact for technologies in the clean energy sector, in national security, with the overriding goal of U.S. competitiveness and providing a significant public benefit for the tax dollars that are spent on the research that's conducted here. In our group, in the technology development group, at a very high level, we're focused on 5 different things. That's number one, is to encourage and stimulate innovation by working closely with our researchers to help them identify promising new innovations that may have commercial applications. And then by managing and protecting the intellectual property associated with those innovations, then by carefully crafting and negotiating licensing agreements and other forms of commercialization arrangements to facilitate the transfer of those innovations out of the lab and into commercial application. And one of these goals is ultimately to help companies sort of advance technology and intellectual property through and beyond the typical research valley of death that many new innovations and new companies face, unfortunately. So we can bring to bear a number of supporting resources to maximize the likelihood of getting past that valley of death into some meaningful and significant commercial applications in the country. And as a group, we are also attunedly aware of and focus on demonstrating national leadership in the technology transfer arena. Now, at a very high level, it is noteworthy to consider where we've come. From the mid-1970s, the value of intellectual assets as a percentage of enterprise value, at least in the S&P 500 companies, has grown considerably from roughly 17% of enterprise value all the way to nearly 90% of enterprise value in 2020. That is astounding. And as one famous management consultant, Peter Drucker, has stated, in the knowledge economy, the key strategic resource is not land, labor, or capital. It is the knowledge along with the ability to mobilize and deploy it. So that's front and center for us. Among the different types of intellectual assets we develop here at INL are a slew of various software innovations. You've just heard of one: databases, inventions, trademarks, in a variety of different areas, from space power systems into the domain of cybersecurity to bioenergy and an entire range of highly specialized nuclear software codes, some of which are available for under various open source licenses, and others are available strictly under proprietary licensing arrangements, but all of which are being developed and made available for the specific purpose of achieving our commercialization goals and objectives. So tech transfer as a business from our viewpoint we believe we've had a significant impact on U.S. industry by, as represented here, we work with a number of companies, both through patent licensing arrangements as well as copyright licensing arrangements. And the bar graph here shows that there's been a steady but significant growth in the number of active licenses and licensees from fiscal year 16 through last year. So I guess we're proud to say that at least, and I would qualify that, at least 50% of INL's intellectual property is actively licensed in some form or another. And we intend to continue on with that activity and to be the partner to industry and universities and other national laboratories that are positioned to take what we've developed and achieve for writing national goals and objectives. Thanks for your time and attention, and let's see if there are any questions that have come in.
Yeah, I saw a question in the chat about on the Fenix website, we have a list of publications that are about to come out. Toussaint, you're still sharing your screen, by the way. And so I responded to that in the chat. We'll add them on the website as soon as possible, and we're happy to discuss, those contributions in the meantime if you want to reach out. I think we have the emails at the top of the chat. The other question from Brian, hi Brian, ask, can you describe how the MOOS tools are used in a complementary way to closed source industry multiphysics software? So MOOS is very flexible in that sense. So there are many ways that you can do that. I'll go to the most straightforward way and then more intricate. The first one is, complementary is you can just do benchmarking cases. So you have a case, you use both tools separately, you see the predictions, you compare them. And then, for example, you can see if there's a gap in one of the tools. And I think that's one way that you can do parallel development of those tools, and that's one way to use those tools in a complementary manner, in my opinion. Another way to do that is to use the wrapping capabilities that we talked about through Cardinal. MOOS being open source or Fenix being open source, doesn't prevent us, or doesn't prevent a company to use it as a way to wrap around a closed source industry multiphysics software and leverage that software as a part of Moose, just like Cardinal does it with OpenMC, etc. So you have a lot of flexibility. You can wrap Moose around closed source codes and leverage them if you have the specific capability in those specific codes. That doesn't exist in Moose. That's something you can definitely do. Casey, do you want to add to that?
Yeah, I forgive me if you already said this. I was typing a response to the chat, sharing Toussaint's email address to another person in the chat. But yeah, you've got these kind of like traditional, like these two extremes, right? The benchmarking where you're doing separate comparisons. You've got what we call Moose wrapping, where you're using Moose APIs or application programming interfaces in order to take the data that you're generating and bring it into Moose. You've also got that stage in between where we can, it's more of like that manual traditional data handling process of creating output, and we've got plenty of interfaces to bring that output into Moose, as well as other INL products like the Deep Links system that allows for warehousing of data and defining relationships between different code products. More than we can talk about today, but I suggest that you search up Deep Links. I can put a URL in the chat. But that's the way that we see as integration with our tool set at varying degrees as possible. And the sky's kind of the limit. The interfaces can be programmed anew and things can be changed and modified, especially with open source tools. So we really believe the flexibility is key. Hopefully that answers the question.
I put the link in the chat for Deep Links, and Brian, if you have a follow-up, don't hesitate. The thing is, in general, if there is a need, we're very open to discussing some of that. As we showed, there's like discussion forums for Fenix and Moose, or you can reach out to us privately, and we can see what we can do to support whatever effort you're having, or see if we can tackle any challenge you're facing.
I'd like to add that we have the flexibility to establish various types of engagements and relationships. So if there's an interest at any level and in any form, please contact us. I'm the principal contact for assisting with the commercialization of this technology, but please feel free to engage with me for tech transfer or tech licensing related needs, or directly with the researchers with any questions. And we have a question here. It's what industry really needs is an open source replacement for expensive software like ANSYS for developing various aspects of robotic/autonomous systems. Any thoughts as a response?
Casey, do you want to try to tackle this one?
Yeah, I'm not very familiar with robotic and autonomous systems as far as applications in ANSYS, but I will say that we seek to be an alternative to these closed source tools. What we want to do is give researchers, engineers, scientists, inventors the ability to have access to these state-of-the-art numerical solvers and underlying libraries, whether they be the various kinds of open source projects, and get out of their way so that they can do this sort of work, whether that be developing on a singular component level, a robotic system that then can be brought together to work in tandem in a simulation, a larger simulation. So I don't know if that answers the thought exactly, or maybe in enough detail that you wanted, but the idea I feel is straightforward, that like these closed source tools, we want to give you a strong pathway to do the science and engineering that you want to do.
Yeah, I'm also not fully equipped to answer that question because I don't have that much experience with robotics and autonomous systems. But Adam, if you wanted to send us an email, we can try to point you to the right person. And Sharon is asking if we'll have a recording of the presentation on the website. And Sean answered yes. Yeah, thank you, Adam.
Yeah, and we agree the UI UX is important, and the one thing that we're working on actively and almost continuously is how we can take Moose-based tools, which, as you saw in some of our descriptions, are kind of command line based. We do have graphical user interfaces, like front ends, available in various stages of development by the community. But that's one thing that we keep coming back to time and again, is how can we take the good things about Moose and the access to the powerful tools and take it another step further, using in order to make it accessible to even more people that might not be as familiar with writing code or using the terminal on their Linux workstation or even their Windows workstation.
Are there any other questions from anyone?
Do you want to make one more point? I realize I just said Linux and Windows. We also are Mac compatible as well. So all three major operating systems in some form or fashion. We use the Windows subsystem for Linux capability in order to facilitate Windows compatibility.
Excellent. So I think we're about at time right now. PC and Casey, thank you once again for a very informative presentation. If we could not get to your question, or if you have additional thoughts or comments, please feel free to share them with us by email afterwards. But thank you again for your participation in the webinar, everyone. And your engagement and interest in our work is greatly appreciated. Again, we look forward to being a resource to the community, and should you have any further questions, please do not hesitate to reach out to us by email afterwards. Thanks again, and have a great day.
Thank you all.
Yeah, thank you, everybody.